feedback, as well as a stellar population sampled stochastically from the IMF, and also the chemistry of the interstellar medium. Using the applied external gravitational potential, I've adjusted the scale heights and the circular velocities of the disks in order to probe as large a range of galactic dynamical environments as I can. And these can be parameterized in terms of the galactic shear parameter on the x-axis here, the gravitational stability on the y-axis, and the orbital angular velocity given by the color bar. And we're able to span around an order of magnitude in each of these. So each square in the parameter space represents an azimuthally averaged population of clouds along a radial trajectory in each of the disks. So now that we have this large population of clouds, we're able to examine how their physical properties correlate with the time scales of the key galactic dynamical processes that operate. And in our Milky Way-like galaxies, we find that these are the time scale for galactic shear in the upper graph here, and then the gravitational freefall time scale in the lower panel. And we can divide the parameter space according to which of the two timescales is the shortest and is therefore expected to have the largest influence on how the clouds evolve. And so, for example, we find that the median aspect ratio of our clouds displays an environmental trend where it correlates with the shear time scale in the shear dominated regime, and then with the free fall time scale in the gravity dominated regime. So in other words, as the influence of galactic rotation increases compared to gravity, the clouds are slightly stretched out along this direction. And we see the same trend again in the internal velocity anisotropy of the clouds, and also in their specific angular momentum in the plane of the galaxy, which also increases with the influence of shearing. However, we find that for the turbulence and star-forming properties, there is no clear environmental variation. So we're able to summarize these results in terms of the significance of the correlation with the galactic-dynamical timescales, where in the green region here, we show that the rotational properties of the clouds do display a significant environmental trend, but in the red area, that the turbulent and star-forming cloud properties are not. And actually, this would be expected because we also find that the clouds in our simulations are at over 25 times the hydrostatic mid-plane pressure, and we actually would not expect these to interact a lot with the environment. However, the H1 clouds in our simulations are only 4 times over pressured, and here it is the rotational as well as the turbulent properties that display a correlation with the environment. And this suggests that maybe in galaxies that have a higher mass, that the molecular clouds will also be nearer in pressure to the mid-plane, and so have a larger galactic dynamical coupling. So I've only talked so far about the static properties. However, we're also able to track the clouds in the simulations over time in order to produce the cloud evolution network here. So here, the time runs from the top to the bottom of the slide, and we can see where the mergers and the splits occur. And then we can look at cloud demographics, for example, comparing the clouds that do undergo interactions throughout their evolution for those that remain isolated throughout their lives. And here we see that the clouds that do undergo interactions tend to have a higher mass and level of turbulence, and also lower star formation rate than those that evolve in isolation. So we can go a step further and look only at the parts of the trajectories that occur after a merger. And here, although we see the mergers do increase the mass of the clouds, they only have a small influence on the level of star formation in the clouds that interact. So, we can also calculate the average cloud lifetime from our evolution network. And here, just by looking at the network, we can see this should be a roughly exponential distribution, as the rates of cloud formation and destruction are constant in time, and the number of clouds is constant in time, which indicates here that the number of clouds we expect to survive for a time longer than time t should be exponentially distributed. So if we then slowly take Monte Carlo slowly walk through the merger history in order to isolate the unique trajectories that correspond with the survival times of individual clouds, we see that, yes, indeed, the survival times are exponentially distributed, which means we're able to get the average cloud lifetime out of the slope. And if we actually do this with the clouds of different mass, we see that there's a steep drop in the cloud lifetime as the mass increases. And this can actually be understood in terms of the median evolution of the pressure and the SFR, which show that smaller clouds tend to need a longer time to collapse. So to larger pressures and levels of poundedness in order to achieve the efficiency of star formation that's required to then disperse the cloud again. And then by degrading the resolution of the maps we use to identify the clouds, we're able to actually look at the scaling relation of the cloud lifetime. And here we see that it's able to be clearly divided into two regimes. So if we're able to resolve the scale height of the gas disk, we're able to resolve the clouds that are actually collapsing and forming stars and being dispersed. And hence we see that the lifetime increases as the size of the clouds gets smaller. However, if we're unable to resolve the scale height, we find the lifetimes of the clouds just converge to the gas disk crossing time. And this is expected because the majority of objects we identify in this case would be vertically confined on the scale height of the disk. So yeah, I think I'm out of time, but in conclusion, we find that the star forming properties of our clouds do not depend on the environment, although those of the H1 clouds at lower over pressures do depend on the environment. Then we find that the molecular clouds that interact are more massive and turbulent and with smaller levels of star formation than those that do not. And that the molecular cloud lifetime obeys a scaling relation. And this depends on the resolution of the maps that are used to identify the cloud. Yep. So yeah, that's it.
Thank you so much for a really fascinating dive into how these clouds form and then evolve and work. We're really grateful. So can we start with a little bit of a question which I believe relates to some extent to the star formation timescale and then like the lifetimes of these clouds, which comes from Floor, which is how and if are stellar winds modeled in this sort of simulation that might come after stars form? What's the treatment when stars are thought to form at the end of a cloud lifetime?
At the end of a cloud lifetime. I'm not actually including the winds explicitly in the simulations. I'm not sure if that's what it, is asked here. If I go back to my simulation slide, I have supernovae and H2 regions, but not winds explicitly.
I see.
Yeah. Yes, no, so I am injecting the mass from winds, but that's just in order to conserve the mass. There isn't any energy or momentum associated with winds here yet.
Interesting. And so when I'm really interested in this idea that you raised, that the turbulent cascade to higher densities is such that the 25 times overpressured clouds, their properties are identical regardless of environment.
Yeah, almost.
Almost identical, which is kind of amazing that something so universal arises out of something so seemingly diverse as these different environments that you've modeled. Can you talk about, so clearly that's not the case with the more minimally overpressured H1 clouds, but can you talk a little bit about like how the environment affects, if it does, the like number or masses or that sort of thing of the molecular clouds that do form?
Yes, so here, you can't see the cursor here, but I'll just exit. Here, the property on the left-hand side is actually the number of clouds per unit area. And yes, okay, this also does have a correlation with the environment. So there is a much larger number of clouds per unit area in the inner compared to the outer regions of the galaxy.
I see. So if, for example, you were shear dominated, you might be less likely to form a molecular cloud. Is that correct?
It seems that way, yes.
Interesting. And then, yes. But once you do, and once you've reached that degree of decoupling from the environment, that cloud might actually be kind of similar to a cloud elsewhere. Is that the idea?
I would say that, yes, that's what the results are showing.
Do you think that means that, in star formation, we always have to sort of simulate the different scales separately because, it's hard to do a star forming simulation that includes a galaxy down to the protostellar cores. So do you think kind of the universality of these turbulent clouds is useful in that regard? Like, does that mean that isolating a cloud and simulating just a cloud is a viable strategy?
I would say that in Milky Way-like galaxies it is perhaps, but I think that as you increase the mass of the galaxy, there might be a greater degree of environmental variation of the clouds. And also here I haven't included spiral arms or any other environments that might also be expected to change the properties of the clouds. Yes. So here, yes, perhaps, but as soon as you increase the mass of the galaxy or introduce spiral arms, for example, I would expect this not to be the case anymore, actually.
Fascinating. Well, we'll be really excited to hear the updates, and we can continue the conversation more on Slack. But thank you for all of your insights and a great talk.
Yeah.
And let's transition.
It's good to be here.
Thank you again.
Thank you. So, okay, our next speaker is Azadeh Fattahi, who is currently a postdoc at Durham and has been also a co-fund junior research fellow there. So before that, Azi has been a PhD student in Victoria and a bachelor's student at Sharif University of Technology in Tehran, Iran. And even before that, she was a gold medalist at the International Astronomical Olympiad. So throughout her career, Azi has been a member of the Virgo collaboration. And so she has been working on this cutting edge cosmological simulations and led the efforts in particular to analyze Milky Way-like environments. And most recently, she has been looking into what happens to the satellite population of Milky Way, the simulated Milky Ways. And I think this is what we'll be hearing about today. So Azi, take it away.
Thanks, Anna. I don't know how you know about my high school history.
Yes, you know, our background checks are very thorough.
We're nothing if not researchers.
Okay, let me share my screen. Does it work? All right, perfect. Good day, everybody. I'm very happy to be virtually with you today to talk about my work in the past year or two. And I hope all of you are finding these strange / difficult times. I hope you're all surviving well. And we're going to hear more about, actually not more after Sarah, about simulations, but about dwarf galaxies and Milky Way, the stellar halo. And of course, I should thank my collaborators who, I guess all these works are with their help, Alice Thiessen and Carlos Frank in Durham and Vasily in Cambridge and the Arepo simulation team that I will tell you a little bit more about that. So the outline of my talk is I'll talk about the Milky Way satellites and the formation of the stellar halos. If I have, that's a published work. And if I have a time, I'll show like maybe 2 slides about what I'm thinking about or working on these days. Very, very brief introduction. I'm sure you're all aware of the standard model of cosmology. This is a hierarchical galaxy formation where most of the gravitating matter in the universe is dark matter. We have a Big Bang at the beginning where the density in the universe is relatively smooth, and collapse of the structure leads to the formation of halos and subhalos. And as I said, this is a hierarchical formation scenario, meaning smaller things merge and accrete and form bigger objects. And this is kind of one of the robust and core predictions of this standard model of cosmology. Here is just a video of actually one of the Auriga galaxy formation. You're looking at the dark matter on the very left, and looking at the formation of basically stars on the very right. And we can see that's actually there's, by the way, you're seeing the hierarchical formation. You see all these little clumps are getting accreted, but also there's a big difference between the formation of dark matter halo versus the formation of the stellar component, which I am going to mainly focus on that today. At present day, that's what the halo on the right, you can see what the halo like the Milky Way looks like with all these subhalos or clumps around it. And we see at least the bigger ones that look like satellites, and we observe them as Milky Way satellites. But the ones that have been accreted in the past gets disrupted. This is just from some numerical simulations in the past, from dark matter only ones from the 2005 Bullock and Johnson to more recent hydrodynamical simulations where we actually have the star particles and we can look at the formation of the stellar halos. So these are another predictions that are from this hierarchical formation that we expect to see this a lot of substructures and this stellar halo that's actually relatively diffuse around galaxies. Observationally, we see this beautifully around the Milky Way. Here I'm showing a very nice work from Anna. We're looking at, well, in the Milky Way, we are inside the galaxy, so we don't have some sort of a bird's eye view we see all the substructures and the streams. If from inside the galaxy, you can see again on the left for the Milky Way, and some galaxies, outer galaxies, Milky Way or another NGC 474, that we see these basically nice structures around these galaxies as stellar halos. And I like to study the connection between this component, which is the stellar halo that are formed from the disruption of dwarf galaxies, versus the population that survive today, which we just saw in the previous slides, population today that survive as satellites of the Milky Way. I'm using Auriga simulations in this, basically, what happened? Is it? Okay. Auriga simulations, basically the results I'm showing are based on these simulations. These are a set of Milky Way halo masses. These are 10 to the 12 solar masses halos, relatively isolated, and they have been run with a galaxy with Arepo and a galaxy formation model that is quite similar to the TNG model. There are slight differences. That is kind of the backbone of the analysis I'm going to show. You're going to see a lot of plots maybe labeled survived dwarfs or satellites versus destroyed ones. So I'll give you kind of definitions of what I'm exactly talking about. Survived dwarfs or satellites, they are more straightforward to define. These are basically, at present day, we observe this, or in the simulations, we find this as bounded structures around Milky Way halos. They have non-zero stellar mass. By definition, I call them galaxies. And in the Auriga simulations here, the plot, you're looking at the luminosity function or stellar mass function of the satellites, which are, again, survived dwarfs, compared to a Milky Way and M31 observation. So we can, we can see that actually at the Z equals 0, basically, stellar mass function is relatively a good match to what we observe. The other population that I will talk about are these destroyed ones that are forming the stellar halo. So they are, I identify them by the fact that they do not have any bound or remaining structure at redshift 0. So they have been accreted at some time ago. I track things back in time. They have been accreted some time ago, but at redshift 0, we do not find any basically bound or survived entity in the simulations. I want to emphasize that if something is destroyed or not, it's a high debate if it's numerical or not. What I want to emphasize, that kind of a conservative interpretation, is the fact that these are objects that have lost a lot of mass, and they contribute to the formation of the stellar halo. Whether a tiny bit of them are remained or not, for the results I'm showing, are slightly irrelevant. Destroyed dwarfs, you can see them as progenitors of the stellar halo. And I'm going to kind of discuss these two populations, whether they are survived or they have been destroyed. So this is similar to the plot I showed before. This is the stellar mass function of objects that survive to present day as satellites. I'm just, instead of Z equals 0 stellar mass, I'm plotting their stellar mass at infall. I can compare that with the population that have been destroyed. Here, the red ones, the blue one is just a copy from the left hand, and the red ones are the population that have been destroyed. We can clearly see that, at least on average, there have been more, in terms of number and mass, more objects that have been destroyed, have been accreted and destroyed, versus the one that have been survived. And then actually I can just combine the two populations to find out basically the total population of objects that have been accreted to the Milky Way throughout its lifetime. And as we expected in the previous panel, most of the population that have been accreted are basically these destroyed galaxies, and survived ones are a subpopulation of that. And relatively, actually, what is nice is that there's a relatively small scatter around the mean of the stellar mass function of accreted objects. And this is basically the result of the fact that when we have a 10 to the 12 solar mass halo, its accretion history within lambda CDM is relatively well constrained. So you combine the accretion history from the halos and subhalos. And when you map the stars to that, because also there is a good mapping between stellar mass and halo mass, we can find basically a relatively narrow range of, or a narrow scatter in the stellar mass function of accreted objects. The fact that there are more destroyed ones immediately brings up the kind of the questions: does it mean the mass of the stellar halo is more than the mass of the survived objects, or the mass of the total mass of the satellites? So at least these simulations predict that there are 3 times more mass that have been accreted and destroyed than the total mass of the satellites. But a lot of the mass goes to the very central region, not a lot, well, some part of the mass goes to the central regions and in the disk. So if I remove that, basically the very central bit or the disk of the galaxy, we find that the accreted mass that have been destroyed and formed the stellar halo is more or less the same order of magnitude, 1.2 more exactly, compared to times the total mass of the satellite. So that actually this is a nice connection between what we observe today and what we expect to see in the stellar halo. The other point I want to point out is the fact that the shape of the stellar mass function is relatively quite similar between these 2 survived and destroyed population. But there is a very strong dependence on the info time. So this is very similar to the previous plot, previous slide, but I divided the stellar mass function into objects that fell in at different times. So survived galaxies, there are 3 bins 2 to 6 billion years after Big Bang. By the way, 0 is Big Bang. 2 to 6 billion years, 6 to 10, and the most recent one that are after 10 billion years. So in the last 4 billion years or so that have been accreted. That looks very different between the objects that are survived at redshift 0 compared to the ones that have been destroyed. We'll see that most of the destroyed ones are actually the objects that fell in relatively early, 2 to 6 billion years. There is no curve for more recent than 10 billion years, because actually there were very few satellites. I couldn't even just plot a curve. It's just a handful of objects that have been accreted recently and have been destroyed. So most of the destroyed ones, as also we perhaps would have naively expected, that have fell in relatively early. And again, the combination of objects, these are the ones that have been survived plus the one that have been destroyed. When we combine everything together, most of the population again is dominated by early info objects, and the ones that have fell in recently are relatively subdominant compared to the other components. We can see what I kind of describe here more clearly. I'm looking at showing the info time of the objects versus their stellar mass at info. The blue objects are again the survived ones and the red ones destroyed. And the lines are the median at a given stellar mass. We can see what I was describing before, that the survived ones, which are existing satellites, fell in relatively later, and the destroyed ones early, quite early. Actually, most of the population fell in the first 2 to 4 or 5 billion years after the Big Bang. The other interesting we see here is there are very few big objects. I mean, big objects being here. This is actually another kind of sign of the hierarchical formation, because the 10 to the 9 or 10 to the a few times 10 to the 9 solar mass dwarf galaxy takes time to form. So most of the ones that have been accreted were accreted relatively later. That is the general trend we see here, that with mass, the 2 curves go higher. And the other very interesting thing is that the survived ones, especially at the high mass end, the ones that have been survived, fell in very recently, almost all of them in the last 4 billion years or so. And that's due to dynamical friction, because big objects get pulled to the center because of the dynamical friction, and they merge very quickly on a very short time scale. So we see the effect of dynamical friction at the high mass end. This bias in the info time has some consequences for some of the observables. Here I'm particularly looking at the metallicity, or in this case, average FE over H of objects versus the stellar mass. So we have the mass metallicity relation here, basically. Destroyed objects, so the average is the red curve, and the survived ones at infall, if I look at their properties at infall, so I'm always comparing the properties at infall. If I compare them at infall, we see that the ones that survived are a bit more metal rich. And that's the consequence of actually a small, at least in these models, a small evolution of mass metallicity relation. So here I am showing, well, again, stellar mass versus metallicity, or Fe over H, and I color code these objects based on their infall time. The ones that fell in early are low, and the ones that fell in later are kind of higher. So thanks, Anna. So we expect this basically trend that this bias in infall time also translates into the bias in the mass metallicity relation. And even more when we look at Z equals 0 properties, because when we look at Z equals 0 properties, some of the objects since infall, they've lost some mass. So in this panel, they move to the left, and they also have been forming a little bit of a star after infall, so they can enrich a little bit after infall, so they go up. So actually, the difference between the destroyed ones and Z equals 0 satellites become even bigger because of this effect. So in the last 5 minutes, I go over some of the stellar halo related kind of science or questions about the formation of a stellar halo from the destroyed objects that I talked about. So in the simulations, we have a lot of power in terms of tracking all individual stars. So what I do is I take in a stellar halo, I track every individual single star to which progenitor it came from. And here is an example on the left. If all the ones that, let's say, belong to the orange curve are all the particles that came in with one single massive progenitor. A blue curve corresponds to all the particles that came in with a low mass dwarf galaxy. So I can basically look at the radial trends of the formation of the stellar halo. And we're looking at enclosed mass in the left and some sort of a mass fraction in shells on the right. And again, blue things are lower mass objects. What we see that in the inner regions, inner 20 kpc or so, basically one or two, at least in this one example, one or two objects are forming most of the stellar halo. But when we go to the outer parts, the very small ones or lower mass objects start to just become important, but the inner regions, or very few objects is needed to form the inner regions. I can kind of summarize this. What I showed in the previous slide was just one example. I can summarize this over all the regal halos. The way I do it is I go to different bins of radius here, for example, 0 to 20, 20, 50, and so on. And I ask how many progenitors do I need to form 90% of the mass. So I basically rank them and I look at how many, the top progenitors, if you want to call them, how many main progenitors I need to form 90% of the mass. The inner regions, we need very few, on average about 3 galaxies to form the inner regions. And in the outer parts, we need more. So you can see clearly the trend with the radius. The other interesting point is that what do these progenitors look like in terms of, for example, their stellar mass? So these are, let's focus on one panel so I can explain what's going on. So I go to basically these main progenitors of the inner region in between 0 to 20 kpc. I ask what is their stellar mass at infall and how much mass they contribute in that region. So if it's 1, it means that one dwarf galaxy contributed 100% of the mass in that region. And if it's, well, 0, very little. And what we see is basically most of the mass in the inner regions are coming from massive dwarf galaxies. These are the ones that I show on the top. And what we see is that, again, at least in the inner regions, things that are below 10 to the 8 or so contribute very negligibly. Basically, the mass in the inner regions, 99% of the mass in the inner region of the stellar halo are coming from relatively massive dwarf galaxies, not the tiny ones. Trend slightly changes in the outer parts. In the outer parts, we start to see that lower mass galaxies also become important. But inner parts is what I like to focus on because that is more or less where we observe, more or less, at least with our current facilities, we don't have a lot of information in the outer parts. In the inner parts, as I mentioned, most of the things are coming from very few objects. I'm just going to skip this dark matter and go into the metallicity. So the fact that most of the mass is coming from very big objects, it affects the metallicity formation of the stellar halo. Here, another one example of one of the halos, and I'm looking at the metallicity distribution of individual, so let's say the individual curves here are stars that came in with different progenitors. The metallicity distribution in this whole halo is in the black curve, and every individual curve is any of those basically progenitors. We see basically there is a mass metallicity relation, which is actually what we saw before. This is the mean metallicity. The mean metallicity changes with mass. This is some sort of a color, the trend you see with color is the mass metallicity. But something that's interesting is even at the lowest mass, at least in this example, even at the lowest, metallicity, still the most massive dwarf galaxies are important. Basically, their mass is so dominant that even at the low metallicity, the probability that the stars are coming from the little ones is low. And that's general across all Auriga halos. This has important consequences because when we typically observe very metal poor stars, we associate them with low mass dwarf galaxies. But at least these models predict that even the low metallicity stars we observe as part of the stellar halo, they are part of the tail of the distribution from the most massive dwarf galaxies. Here you're looking at the, let's focus on one curve, again, the inner region 0 to 20 kpc, which is blue. I'm looking at the probability that a star is coming from a progenitor of 10 to the 9 or a progenitor of 10 to the 6 solar mass. So we can see that at Fe over H below -2, the probability is more than 50% that the the metal poor star is coming from the basically dwarf galaxy that's relatively massive. So that's the neat prediction that in the future, hopefully I can follow it up and combine with observations, we can see if this is actually true or not. And because I'm getting basically close to the end of my time, I will just simply say one word about what I'm doing these days is I'm looking at the spin of the stellar halo, which has been measured, that has been relatively low. And I'm connecting it with the accretion history of the Milky Way, that this Gaia sausage prediction that has been going on, saying that Milky Way has had this radial merger in the past. I'm connecting these two, and I use Auriga simulations to select the ones that look like do have these highly radial stars, and I'm connecting the spin of the stellar halo to the formation history. I don't have the time to go to the details, but just to give you a flavor of things I work on these days. And as a wrap up, the takeaway points that hopefully I'd like to stick with you is the fact that the destroyed population of dwarf galaxies, destroyed quotation, the ones that have lost a lot of mass and formed the stellar halo, are dominant over the ones that we observe today. And most of them are failing relatively early compared to the survived galaxies. And this bias in the infall also reflects in the a bias in the mass metallicity relation we observe. And then on the formation of the stellar halo, I would like to emphasize that the inner regions, we need very few massive dwarf galaxies to form the inner regions. And the low mass dwarf galaxies are almost irrelevant in the inner region. And that also has a consequence for metal poor stars, that at least in these models, we predict that the metal poor stars are coming from high mass dwarf galaxies rather than the very low mass ones. And I stop here to take questions.
Thank you so much.
Thank you.
Thank you.
So can we start by talking a little bit about where, and this is something that you're alluding to in even in these last bullet points, but like where destroyed objects or disrupted dwarfs end up. So do the ones, so Anna was asking, for example, do the disrupted satellites that end up in the central part of the galaxy, do they become a bulge component, or do they contribute to something separately?
So here to kind of illustrate that what's going on. So here we are looking at on the right, we are looking at all these stars that are coming from different destroyed dwarf galaxies. The ones that are coming from massive objects, like the yellow or the orange, reddish colors, these are relatively massive dwarf galaxies. And here, this is a mass fraction, but another way of looking at it is some sort of a density profile. We can also see it on the left. The orange is enclosed mass. The orange one has most of its mass in the inner 20 kpc or so, but the little ones that have been destroyed are in the outer skirts. So the ones that are in the inner regions, I think depending on what one, as you can see, these go down to, I stop at 5 kpc, but it goes even further down. Just naively, if you want to describe that the inner 5 kpc is bulge, actually in these very massive ones, they deposit a lot of their mass in the inner, let's say 5 kpc or so, which is bulge. And some of them go to the disk. I haven't distinguished here the ones that become some sort of a co-rotating. It's a small population, but there is some of them that become co-rotating with the disk and they become ex situ disk stars, at least in these models. But a rule of thumb, the bigger ones, because of dynamical friction, they get sunk to the middle. They deposit a lot of mass in the middle, and depending on what you define as bulge, if it's the central, whatever, 4, 5, 6 kpc, they definitely contribute significantly to the central bits. I hope I answered that question.
So then can we talk about how these dwarfs add up to the like properties of a given component? So in particular, the halo. So Anna is also asking, can you tell us more about your most recent work on the rotation of the halo, and how common is it for a halo to be uniformly rotating? And are there cases where rotation has opposite like sign essentially, or just slope as a function of radius? And I guess as I was thinking about this, it's almost like, what if we had Gaia in each of your simulated galaxies? That came to mind as you were showing us sort of the plots of the observables, essentially.
So going, particularly because Anna asked about the halo spin and the work that I'm doing, these are relatively preliminary. I'm literally working on them these days. So this is just basically, if you were going to observe the spin of the stellar halo, this is rotation of the stellar halo in these various samples. On the left and right, I simply divide them into, from an earlier work of mine, I was identifying some of these Arepo galaxies that do have these sausage-like components, like this one actually, let's see. So this one, we're looking at the radial velocity versus azimuthal velocity. This had this, what people call Gaia sausage, which is very radial interstellar halo. But basically, most of the interstellar halo is dominated by this very radial component. So when I basically look at the divide the sample into the ones that do have this Gaia sausage versus not, here's the distinction I'm looking at. The ones that do have this Gaia sausage or this very radial component, they also have little spin on average, small azimuthal velocity versus the rest of the sample. As you're seeing, actually you can see the slope that you were asking about. They can have various slope. Typically the ones that have close to zero velocity, they're also more or less flat. But the question had one more part. Did I answer that?
Yeah, I think you answered all of them.
Oh, okay.
Thank you so much.
Am I right that Josh, you had a question?
Yes. Did you consider the contribution from a much larger primordial population of globular clusters, which has been talked about a lot over the last several decades or more? If you have a very large population, why do they not contribute to the halo?
Well, the short answer, if I have looked at it, the short answer is no. We do, in these simulations, these are cosmological ones, we do not directly, of course, have globular clusters. So I cannot directly kind of show anything. My gut feeling is that the total mass, because one has to look at the total mass that has been accreted. Let's say when you accrete a dwarf galaxy that's 10 to the 9, you would need how many? 10,000s of relatively massive globular clusters to contribute similar mass. Whether that is reasonable or not, to be honest, I leave it to those who look at globular clusters formation and do we expect that we accrete about, I don't know, 10 to the 4 globular clusters in the history of the Milky Way. My gut feeling is that the contribution from dwarf galaxies are, in terms of mass, their contribution is dominant over the mass from globular clusters.
I think some of the earlier ideas were that the globular clusters weren't accreted, but rather formed in the galaxy as we think the globulars we see now did. So the question becomes, if there was a very much larger population that formed and most of them have been disrupted, what is their contribution to the halo?
Fair enough. And I'm afraid that I cannot directly respond to that, at least using these tools. But that's a very interesting questions. And we see streams from globular clusters. So they definitely contribute to the stellar halo. But I think quantitatively, we don't know, and hopefully we'll know at some point soon.
Thank you.
Well, Azadeh, thank you so much. There's a couple of, I think, really kind of fascinating questions about how feasible it is to take the next step from understanding these correlations to then sort of reverse engineering almost, or like reconstructing the merger history of a given object from these sorts of properties on the Slack. But I think they might be a little bit more in depth than we have time to dig into in the next minute or so. So I think we should close now, but we hope that you have a few moments to follow up.
Sure, yes, I'll have a Slack open for
wonderful
to respond.
Well, let's thank both of our speakers for some really wonderful talks. I learned a lot today, and we're really grateful for your time and for joining us.
Thank you.
Thank you all. And we'll see you next week.
See you next week, that's right.
Yeah. Bye.
Bye.
Bye, thank you again.
Thank you, guys.
Thanks, Anna.